Good morning, everyone. We'll start in just a minute or so. Okay, let others also join in. All right, before I start, do you guys have any questions? Any questions about the previous session? I just took one session so far. Okay, no questions then. All right, let's do a quick recap of what we had discussed. I'll only talk about the algorithm. So we were looking at an algorithm called as k nearest neighbors. Okay. Now, in this algorithm, also called as KNN for short. Okay. So in this algorithm, what we do, imagine we are given a data set. Okay, let's say if this is, let me call this as my training data set. This is the data set I'll be using for making predictions. Okay. So use this data set for making predictions. All right. So we actually discussed univariate regression. So we had one input feature. I believe we looked at the age of the people, and we then I think we tried to estimate their height, something like this we did, or we took height, or I think as input, and we estimated the weight. Does anyone remember what did we do? Like what we did last time?
Yes, sir. Height and weight.
Height and weight. Okay.
Yes, sir.
Okay, let's look at that. Okay, so we took height as the input and weight as the output. This was the input, and this is your output y. So please note that output is typically associated with this notation y. Okay, and this input, I'm going to write it as with the notation capital X. And the subscript will tell you what feature number it is. So I've written it as X1, which means it's the first feature. Okay. So I have some values. I have some values. So I'm just taking some random values. Okay. Let's say 12. I mean, it's not exactly for a human, but let's imagine. Okay, let's say this is what it is. Yeah, maybe say 18, say 19, let's say 23, the 31. So this is 34. Say 48.6. Okay, let's say this is the data that we have. Now, imagine we are given this another test set. Okay, let's call this as a test set. And this is the data that I'll be using, okay, for evaluation, for evaluating your model. You can assume it like this. See, when you are given a data set, right? This would be your big data set where you have this input feature as this height, okay, and the output as this weight. Okay, you'll be given a big data set in total. Okay, you'll be having many samples. All right, so what we do is we divide this data set into two parts: training data set and testing data set. You can call it training examples or test examples. Okay, so training data set is this one that is used to make your predictions, and test data set is this one, okay, that is used to validate the model's performance. Okay. Now my question is this, please listen to this very carefully. Let me just make another column here. Give me a second. Okay. All right. So these are the actual values. These are known to you, by the way, because once you split this data set, right? So some of the examples go to training and some of the examples go to testing. So you know their actual values. Okay. You know their actual values. All right. Keep this in mind. You know their actual values. Okay. So I have a small question here. Imagine they say I have a sample and the sample value, the height of this particular individual is maybe say 13. And if you're using the concept of say one nearest neighbor, what would you predict? What would you predict? If the sample has the height as 13, what would you predict?
13.5.
13.5. So this is the predicted value. I'm going to call it as y hat. So y hat is denoted by, it denotes the predicted value. So we are doing one nearest neighbor. I'll write it. Okay, this is the value which comes out from one nearest neighbor. So if I ask you, let's say if the actual value was maybe 16, okay. So how much mistake that you made? If I ask you how much mistake that you made, what would you say? So for this very first example, let's call this example as x1. So for this example x1, how much mistake was there?
2.5.
Yeah, so the actual prediction was 16 and the predicted was 13.5. Okay. So we have to come up with some metric to evaluate this, right? So we discussed some metrics. Do you remember we talked about absolute error? We talked about squared error. These are the things that we had discussed last time, right? So what would be the absolute error? 2.5. What would be the squared error? 6.25. Does this make sense? Yes or no?
Yeah.
Make sense? So you're subtracting. So absolute error is nothing but y minus y hat, and you're taking the absolute of it. Okay. Squared error is nothing but y minus y hat, and you're doing the square of it. Okay. So you can do it for the first sample. Similarly, let's do it for one more sample just to illustrate this. So let's say that, okay, this is maybe say 15. Okay. So what should be the output now? Maybe consider this to be 20. What should be the output for the second sample? If the height is 15.
18.
18. The prediction would be 18. You're looking at the closest neighbor from these heights. And the closest neighbor of 15 is 16, right? Okay. So your actual value is 20, predicted is 18. So this is 2 and this is 4. Okay. Let's consider two samples for now. So if I ask you, what is the sum of absolute errors? What would you say?
X1 plus X2.
X1, X2 denote the samples. So we will say that it is the absolute sum of the errors for X1 and X2. Okay, I can write it like this: I equals to 1 to 2, because I have two examples. I will do this: yi minus yi hat. This is the sum of absolute errors, right? Yes or no? This number is 2.5 plus 2, which is 4.5. Okay. If I ask you what is the mean absolute error, what would you do? This is just a recap of what we had done last time. You will divide sum of absolute errors by what number?
Number of records. Number of
records. So what is the number of records right now?
2.
2. So in this case, this would be 1 by 2 of multiplied by 4.5. So this is 2.25. Okay. So this is mean absolute error. In the same way, can you compute sum of squared errors? In the same way, can you compute sum of squared errors? You can, right? Do I have to do this or not? You can do this, right? You just have to add these two values, right? So this is sum of squared errors. I think we discussed it in the last time also. This is just a recap of everything. Okay. And we can do mean squared error. These are the things that we had discussed last time. Okay. I have a question here, and the question is this. If you look at all these metrics, what would you say? Lower the better or higher the better? So all these metrics that we have seen, sum of absolute, mean absolute, sum of squared errors, sum of mean squared errors, what would you call these metrics? I mean, are they lower the better or higher the better?
Lower the bit.
Lower the better, right? Because you are measuring the error, measuring the mistake. Okay, lower the better. Okay, keep this in mind. So if any metric is there which has a low value and it indicates a better performance, that is called as a negative metric. In general, in machine learning, if a metric is, giving you a small value and it indicates a better performance, that is called as a negative metric. Okay, that's just one terminology that you need to know. I'm going to show you one more metric, which is quite popular. I don't think we discussed this the last time. This is called as R2 score. Did we discuss this metric?
No, sir.
No.
This is also called as R squared, by the way. Okay, you can write it like this. R squared score. Okay, also called as R squared or R2 score. Some people also call it as R2. Okay, all right. Now, what is this? Let me just, I'll write the formula and then we will discuss what is the range for it. Okay, can you tell me what is the range of each of these metrics? All these metrics that you have studied, what are their ranges?
Zero to infinity.
0 to infinity. Okay, so all of these metrics, they are in the range of 0 to infinity. Okay, let's look at one more metric. This is a positive metric, by the way. Higher the better. And you will see that why. Okay, let me first write the formula and then see this. Okay. Assume you have n examples. Okay. This is the formula that you have. Okay. So this y bar is the actual average. Okay, average of y values. Average of the actual values. Okay. So yi denotes actual values and yi hat denotes predicted value. My question is this. Okay, let's say if you have an ideal model, what can you say about this highlighted entry? What will be the least value possible for this?
0.
0. It's a sum of squared errors. The least value is 0. So if this numerator is 0, what should be this r squared? If numerator is 0, what value do you get?
1.
1. So ideal model, if you think about it, okay, do you realize that this whole term, the fraction that you see, it is subtracted from 1, right? Do you realize that this fraction is always going to be positive? Yes or no? There is a square term. Focus on these. Will this fraction ever be negative? Numerator by denominator, if you do, will this ever be negative? Is numerator always positive? Do you agree? It is 0 to infinity. Okay. What about denominator? Will denominator ever be negative? You are subtracting the mean from every actual value and then you are squaring it up. Will it ever be negative? No, right? So this fraction is going to be positive always. You are subtracting it from 1. Okay, you are subtracting it from 1. So it can go negative also. 1 minus of that can go highly negative if you think about it. Okay, depending on what this fraction is. Okay, depending on what this fraction is, you are subtracting 1 from it. One is you are subtracting this fraction from 1. So the highest value that is possible is 1, and the least value is possible when numerator is 0. Does that make sense? So for the ideal model, the best value that you can get is 1. Okay. Okay. What would happen if you have a worse model? What can you say about the numerator? Will it be big or will it be small? What can you say about the numerator? Will it be big or will it be small? The numerator I'm asking, only the numerator, this term.
Big.
It will be very big. It can go up to infinity, right? But what about the denominator? See, denominator is going to be a constant, right? Yes or no, for a given data set. Is there any predicted aspect here in the denominator? Don't you think y bar is a fixed term given for a given data set?
Yes.
Okay, and yi is just the actual value, so it will be a constant, right? Once the number is decided, it is not going to change. But if you have a verse model, the numerator can actually go up to infinity. So infinity by any number is still a very high number. Let's say infinity. So what do you think 1 minus infinity can go up to? Minus infinity. Does that make sense? Yes or no? It can go up to negative infinity, right? For a bad model, for a worse model. Okay. Okay, let's talk about one more scenario. Okay, when do you think this fraction becomes a 1? I'm only talking about the fraction right now. When do you think this fraction becomes a 1?
When
When?
the same as the mean.
Yes, absolutely spot on. When yi hat becomes equal to y bar, which means that every prediction is equal to a constant. So regardless, can I say that regardless of the input? Okay. So regardless of the input, if you always predict the output as the average value, don't you think it's a constant model? Yes or no? Does that make sense? See, you are saying that, see, what is yi hat? It is the prediction for the ith sample. You are saying that it is fixed. It is the same for the first sample, the second sample, third sample, fourth sample, and so on. Yes or no? Which means that the input features don't matter. Okay. It's a constant model. Okay. It's a constant model. So do you think if a machine learning model is there which always says, let's say the answer is 2, is it a good model or a bad model? Whatever you give it, it will always predict the answer as a 2. It is a good model or a bad model?
That model.
Bad model.
Bad model.
Bad model, right? Very bad model. It ignores your features, basically, input features. Okay. It always says the output is y bar. Okay. So if you think about it, 0 is somewhere, I mean, here, I mean, in between this range, minus infinity to 1. Okay. And this is also one of the bad models, which is this constant model. Okay. All right. So our goal is to be very, very close to 1. Okay. As close as we can get. So this R2 square is a positive metric. What it measures is, we also call it goodness of the fit. How good, okay, how good the model is fitting to your data. Okay. So this is one such positive metric which people use to determine if a model is good or bad. Okay, just like other metrics, negative metrics that you have seen. Okay. Now my next question is an IQ question. Okay, please think about this. How do you convert a negative metric to a positive metric? See, you have sum of absolute errors, right? Look at the formula of sum of absolute errors. Okay, this is sum of absolute errors. It will always be positive because there is absolute sum. Okay, how will you convert it to negative? I mean, can you make it a positive metric? Higher the better. Currently, it is lower the better, right? What change will you do in this formula so that it becomes lower the better?
Square of that number.
Even in that case, it will be still lower the better. Even in that case, it will still be lower the better. Okay, let me just give you a small example. With this, it will be easier. Let's say there are two models, maybe say k nearest neighbors with k equal to 1. So this is one nearest neighbor. And I have another model, say 3 nearest neighbors. Okay. So one nearest neighbor gives me the say sum of absolute errors as 10. And this one is 20. Which one is better?
One nearest.
One nearest neighbor
Yeah.
is far better, right? Lower the better. Okay. Now think of what you can do to this value 10 and 20. Okay. So that higher the better it becomes. Currently it is lower the better, right? Yes or no? Currently it is lower the better. So my question is this: what change would you do to this sum of absolute errors? Then it becomes, higher the better. Okay, one simple idea that you should, you should all have this idea, right? If I have a value which is lower the better, don't you think I can take the inverse of it?
Yes.
Okay, so then it becomes higher the better, but there is a problem. What is the problem? Sum of absolute error can also be 0. Will that be defined in that case? No, right? Okay, what if I do this? 1 by sum of absolute errors. What will you get? 1 by 10 and 1 by 20. Which model will you say is better now? It is still one nearest neighbor. You know that one nearest neighbor is better, right? But what is the value 1 by 10? 0.1. What is this? 0.05. Which is better now? This is higher, right? Yes or no? Okay.
Yeah, yeah.
So one thing that you can do is take the inverse, but there's a problem. The problem is sum of absolute error for a model can be 0 also. In that case, it will not be defined. See, it will always be positive. Okay, but if it is 0, it is not defined. So can you think of something else instead of taking the inverse? Okay, instead of taking the inverse, can you do something else? This is an interview question. If you cannot answer this question, let me tell you, you will not be selected. Okay, I will not select you for sure if you cannot answer this simple question. It's a simple maths question. Okay, I'm pretty sure if 10 kids are there, okay, sitting, out of those 10 kids, one kid can answer it, who has done some 5th level maths. Think.
Sir, can you repeat the question, please?
The question is, see, currently I know that sum of absolute errors is lower the better, right? So I want to modify the sum of absolute errors in a way such that the value that I get, okay, the value that I get is indicative of higher the better. Higher value that I get should indicate better performance. What change would you do in this sum of absolute errors? See, currently I showed one method that I can take the inverse of it. So inverse will give me a higher value, but this is not defined when sum of absolute errors is 0. So there is a problem in this case. In all other cases, it works. Okay. But like when sum of absolute error is 0, this metric will not be defined. It will go up to infinity. Okay. Think what you can do. Okay, let me tell you the answer. Just put a negative sign in front. Let's call it negative sum of absolute errors. What happens now? Which is higher? Minus 10 or minus 20? Which is higher?
Minus
Minus
10.
10.
Okay, this is a very simple question that you asked. See, I'm not trying to discourage or anything. I'm just letting you know these are the kinds of things that they will judge you on. Your understanding of like the concepts that you will see. Okay, so this is negative of any negative metric. Okay, we'll make it positive. Does that make sense? Yes or no? Is this clear? So you can put negative sign in front of the metrics that you have seen, and they will become positive metrics. In that case, higher the better. All right. Why am I telling you all this? You will see that in the implementation today. All right. There are some functions which do not accept negative metrics at all. And because they are defined generically, so all the metrics that you will use, they will use positive metrics only, higher the better. Okay. So there are some functions which internally compare multiple models and give you the best model in return. How do they do that? Then because they have to know, right, if it is higher the better or lower the better. Okay. So if you make every metric as positive, okay, if you make every metric as positive, then you can easily compare. It is higher the better. If there are some negative metrics, if there are some positive metrics, then we have to, I mean, do some manipulations, right? Because the function only accepts only one kind. Or you have to put an argument in the function saying that, okay, this is a negative metric. Okay, there is no such argument by the way. So you have to modify everything to positive. Okay. Now, so we had discussed the example for univariate. Let's discuss the example for multivariate. Okay. So let's take two input variables, age and say height. And let's try to determine the weight. Okay. I have a simple question. See, age we typically measure in years. See, I will keep all my classes as a form of questions so that you understand and get the best out of it. Height we are going to measure, say, in centimeters, weight in probably kilograms. Okay. So I will just take some random values just to illustrate something. Okay. So this is A1, this is A2, this is say Y1, this is Y2, this is Y3. This is B1, B2, C1, C2. Okay. So let's try to understand something. I give you a sample. Okay. Let's say this sample is say D1, D2. Yeah. This is one sample. So the age of this person is D1 and height of this person is D2. All right. My question is this. If I ask you that you are going to do two nearest neighbors, what you will do is you will try to find the distance between this D1, D2 and the 3 points, right? Yes or no? Does that make sense?
Yes.
Okay, let's call this point as the test point. Okay, so you will try to, or rather, I mean, I'll define it generically. If I want to find the distance between 2 points, xi and xj, okay, where xi is, I will make it generic. Okay, it can be any number of features. Okay, it can be any number of features. So let's say xi is a1, a2 up to say ad, and xj is b1, b2 up to bd. How do you compute the distance between multi-dimensional points? Now that you have multiple features, how do you compute the distance? Okay, if there was one feature, what would be the distance?
A1
If there
minus
was
B1.
a1 minus b1, but don't you think distances are always positive? So you will take the absolute, right?
Yeah.
Yes or no? Distances, please note that a distance metric, whenever you say a distance metric, is always positive. Okay. There are 3 rules for a metric to become a distance metric. Not going into there. Okay. If you're interested, you can read about it. Okay. So this is one way to measure the distance. Okay. This distance metric is called as Manhattan distance. Okay. So this is for one dimension. Don't you think we have to do it for the other dimension also? And so on till for all the d dimensions. Does this make sense?
Just one question over here, Sanam.
Yes.
Like xi is, for example, my age feature.
Yes. No. X1 is the age feature.
X1 is the
X-
age feature.
yes.
Xi is my test value for age.
Okay. Forget about test. Just think about how do you compute the distance between 2 samples. If I give you these 2 values, A1, A2 and B1, B2, how do you compute the distance between them?
A1 minus B1, A2 minus B2.
That's what we are doing. Don't you see that?
But my thing is like xi is value. Xi can have values A1, B1, C1, D1, like so on.
Yes.
Column wise.
Yes. So
So xi here, it's like you have given xi can be A1, A2 till AD.
I've just mentioned, see, I'm just trying to show you for a given. So this is the data that we have, right? So far. Okay. Let's imagine you could have D features also. See, I'm just trying to generalize something. Okay. Instead of doing it for 2 features, then I have to write it for everything, right? So I thought maybe it is better if I write it for everything. Okay. If you have 2 features, okay, you do it for, so this would be up to this point. Does this make sense? If you have two features, this would be up to this point. If you have more features, you just keep on doing it dimension wise. Does this make sense?
Okay.
See, what is this iterator going up to? What is this index going up to? The number of dimensions. D is the number of dimensions, the number of features.
Hmm.
Okay. So you are going to take the difference between every dimension, take the absolute of it, and then you will sum it up across all the dimensions. Is this clear? Ask if you have any doubts, ask.
No, it's fine. It's fine. It's okay.
Fine. Okay.
Sandran, can you
Yes.
please, go again with this Manhattan distance once again?
Yeah. Okay. Let's say you have one feature. Okay. Imagine there are two samples. Okay. Let's say one of the sample has a value whose age is 10, and the other sample has a value whose age is say 20. How do you compute the distance between the two?
As you said, A1 minus, sorry,
B1.
XI
So,
minus
so for
XI,
this example, what would be the distance?
10,
10 minus 20, the absolute of this,
Okay.
which would be 10,
10, yeah.
right? Makes sense. Now think of one more feature. Okay. Let's say I have age and also height. Okay. So I have two features now. So age is 10, height is maybe say 148 inches, 148 centimeters. Maybe the other person has age 20 and the height of this person is 163. So what is the distance between these two samples, Xi and Xj? 10 minus 20, absolute
Yeah.
of it, plus 148 minus
It's
163.
163, yeah.
Does this make sense? Is it
Yes.
clear? Okay.
No,
All right.
yeah, yeah.
Okay. So that is what we are doing across all the dimensions, across all the features. Okay. Let's look at this. So there are a few other things that you should know. Manhattan distance is also called as L1 distance. Okay. The name for this is also L1. This is also called as city block distance. There's some names for it. Okay. L1 city block. Okay. One more distance I'm going to define, which is called as the square distance. See, all distances have to be positive, right? So what change can you do to this A1 minus B1 so that it is positive without using the absolute?
Square.
Square it up. Okay. And that is why it is called a square distance. So you will be doing square of A1 minus B1, A2 minus B2, and so on till all the features. And then you are summing it up. Okay. You can write this as summation I equals to 1 to D, AI minus BI whole square. So this is the distance between the two samples, Xi and Xj. See, please note that if you have more than one feature, okay, if you look at this, single vector, okay, this is also called as a vector, by the way. This is also called as a vector. So you are comparing the distance between the vectors now, multi-dimensional features. So if a sample has more than one feature, it is called as a vector. Okay, vector means more than one entity. That's what it means. Okay, so you are now taking the distance between the two vectors, two samples. Okay. Now, please note that there is another term which is called as Euclidean, and Euclidean is nothing but the square root of this square distance. Okay, so if you you'll put square root of this summation I equals to 1 to D, AI minus BI, this is whole square. Okay, the square root is power, it is the pth root, the square root 1 by 2. Okay. Now, let's discuss one more, which you will see, which is called as Minkowski's. Have I discussed these before or not? Have I discussed these before?
No, no.
No?
No,
Okay. All right. So this is A1 minus B1, the absolute of it to the power P. A2 minus B2, absolute of it to the power P. And so on till AD minus BD, the absolute of it to the power P. And then you're going to take the pth root. You're going to take the pth root. Can you tell me what will happen if P is 1? What is this equivalent to?
Manhattan distance.
Manhattan distance. Okay. And if P is equal to 2, what is this equivalent to?
Euclidean distance.
Euclid.
Euclidean distance. Spot on. Okay. Now, the most important question. Okay. And this is what will probably confuse some of you. Okay, let me ask this in a easy way. What happens if P is infinity? Okay, let me ask you this. Can I say this component is responsible for the difference in the first feature? Yes or no? This is responsible for difference in the second feature. Does this make sense? Yes, people. Is this clear? Now you're taking the difference of this, taking the absolute and raising it to the power infinity. Which of these components do you think will contribute the most? You're raising it to the power infinity. So which feature? Okay, okay. Let's talk about age and height. Okay, let's talk about age and height. In general, which feature do you think will contribute more towards the distance? Age is in years and height is in centimeters. Which feature do you think, if I raise the difference to the power infinity, will contribute more?
Height.
In general, height, right? Does that make sense? Because, okay, why is it that the height will be more? Think. You have a valid reason for it. Your answer is correct. Okay.
The range is more.
Range is more. Okay. So can I say that if a feature, okay, has, you can say that if a feature has relatively a bigger range with comparison to another feature, that feature will always contribute more in the distance in general? Yes or no?
Yes.
See, the samples can also change, right? The sample values can also change, but more or less, this feature will always contribute more. So can you tell me, if I raise to the power infinity, okay, so you're raising to the power infinity, can I say that only that feature will contribute, which has the maximum difference? Yes or no? Only that feature will contribute, which has the maximum difference?
Yes.
Okay, and this is defined as the maximum of this absolute of A1 minus B1, comma A2 minus B2, comma A3 minus B3, and so on. Okay. So basically, you're trying to find out the feature difference, which is the maximum. That's what P equal to infinity is. Okay. This is called as the Chebyshev distance. Okay. Now I hope you have understood this, how this maximum is defined. Okay. So whichever feature difference is the maximum, okay, that is the distance. That's what P equal to infinity means. You are not computing the infinite distance. You are just looking at the feature difference, which is the maximum. Okay.
Sir, just one question.
Yes.
So we are all these terminologies that you have discussed is related to the k neighbors.
Yes.
Okay.
You will see everything in k nearest neighbors when I implement it for multivariate data. All of these things will be useful there. Because see, currently what we are doing is we are not specifying what distance metric to use, right? So k nearest neighbors internally, when I'm implementing, I showed you the implementation in the last class, right? Basic implementation. Do you remember, did I specify any distance there? I did not, right? But it must be
Yes.
computing distance internally. How does it do that? Let me tell you, the default value is Euclidean. Okay. So we will see all these things. You can specify it in the method when you are calling k nearest neighbors. Okay. Whatever I'm discussing today, we will see that in the implementation. Okay. Okay. So this was about distances. Now there is one more thing. Okay, there is one more thing. I hope you have realized. Okay, if I'm computing the distance, that feature becomes dominant whose range is more. Yes or no? When I'm computing the distance, that one feature whose range is more can become dominant. Yes or no?
Yes.
Okay.
Yeah.
So don't you think that I have to scale the features before I even compute the distance? Otherwise, the difference for one particular feature would be more, and that is contributing the most, right? Okay, think about, I add one more feature, say salary. Don't you think the difference between age and height is currently, say, So imagine the salary of this first individual is 0 because this is just a 10-year-old person. And maybe the person who is 20 years old is earning a salary of say $100,000. What do you think the distance would be? 100,000 plus 15 plus 10. Where is the most distance? 100,000. So the difference in the salary is so much, it overshadows the other two differences. So don't you think we have to scale these features? Yes or no? If the features are not scaled, one feature becomes dominant, right? What if I ensure that all the feature values for every feature are in a given range, maybe say 0 to 1. I will modify the feature values such that every feature value is now between 0 to 1. So the maximum value is 1, minimum value is 0. Does that make sense? I should do this, right? Otherwise, one particular feature is going to contribute the most towards the distance, and other features will be overshadowed. Okay. Then what is the purpose of having those features? There is no purpose of having those features, right? In that case, you just keep that one feature, which is the most dominant. But that will not give you good results. Alone, that will not give you good results, right? So it is wiser to scale the features. Okay. So this concept is called as feature scaling. Okay. There are two types of feature scaling, which we'll discuss today. Have you guys been taught normal distribution, Gaussian distribution? Has this been discussed before?
Yes, sir. Normal distribution
Has been discussed, right? Okay, great. Okay. I will use that in the next 10 minutes. Okay, but let's talk about feature scaling. So we want to restrict the feature values in a given range. That's what the motive is. Okay, we want to scale the feature values. So let's see one simple way to do it. Okay, imagine I have a feature. Let's say this feature is maybe say some feature x1 or some xi feature. Okay, this is one feature, one column from your data set. You have many samples. Let's say you have these 5 samples. Okay, and the feature values are say 1, 2, 3, 4, 5. I'm taking small values. Okay. Now I want to squish this in the range of 0 to 1. So which value do you think should go to 0? Which value do you think should go to 0?
1,
1. And which value should go to 1?
5.
5. Okay. As simple as that. Okay. We will do it for every column now. Okay. The same concept. Whatever the feature values are for this other column. Let's say you have height. This was age and the other feature was height. You will do it for height also. Okay. Every feature value will now be squished between 0 to 1. That's what we are trying to do. Okay. Let's see how to do that. Okay. And what will 2 be? 2 be a value greater than 0 and less than 1, right? Okay. Intuitively, what do you feel 2 should be? Intuitively, what do you feel 2 should be?
0.1.
0.1 or 0.2?
0.2.
0.2. Okay, you will see that it will come out that. It will come out to that.
0.25.
0.25 or 0.2? 0.25. 0.25. Absolutely spot on. 0.25. Okay. 3 should be what? It is exactly in the middle. 0.5. 4 would be 0.75. You will see that. Okay. Let's see how. So what you do is, if you want to scale any value, okay, if you want to scale any value, first what you do is find the minimum and the maximum from this feature xi. So minimum is 1, maximum is 5. Okay, find this minimum and maximum for the given feature. Okay, so now you're going to scale any value. Which value do you want to scale? Tell me. So I'll write the formula first for you. So value minus minimum divided by maximum minus minimum. Okay. Which value do you want to scale?
2.
2. Okay. So value is 2. What is the minimum? 1. Maximum minus minimum is 5 minus 1. So this is 1 by 4. 0.25. Okay. You do it for minimum. Okay. If value is 1, what is the answer? If you want to scale 1, what is the answer? 1 minus 1 divided by 5 minus 1. 0. And this is what you want, right? You want 1 to go to 0. Okay. Let's say you want to scale 4. So 4 minus 1 divided by 5 minus 1, and this is 0.75, 3 by 4. If you do it for 3, you will get 0.5. So is this clear? How you can scale the values between 0 to 1?
Yes, sir.
Okay. All right. Now, this is a simple concept. Okay. Why just 0 to 1? I want to do it in the range of, say, A to B, any given range. Okay. Let's say in the range of A to B. A can be any number, B can be any number. Okay. Give me any number for A and any number for B. Give me any number for A and one number for B. I will scale it in that range.
10 to 50.
10 to 50. You can even
10
have A to be negative also.
minus 10 to 10.
Okay, let's say minus 10 to 10. Okay, you can, okay, minus 10 to 20, so that we have a distinction. Okay, you can do it between any range. Okay, as long as B is greater than A. Okay, as long as B is greater than A. This is important. If B is not greater than A, then there is no sense of range. Okay, all right, let's see this. So, okay, which value should go to minus 10?
1.
1. Keep this in mind. And which value should go to 25, the highest value? Okay, you will see that will happen. Okay, I'll just write the formula and you can see why this happens. Okay, so okay, initially when I squished it between 0 to 1, when I squished these values between 0 to 1, okay, where did 1 go to? Where did 1 go to? 0, right? Okay, so I'm just, and now where should 1 go to? This A. Yes or no?
Yes.
Okay, so if I'm going, see, I have to add this A. If you think about it, add this A to this value minus minimum divided by max minus minimum. Yes or no? Does that make sense? Okay. But now we also have to scale the data in this range of A to B, right? You have to put every value in this range. Multiply this factor by B minus A. Multiply this factor with B minus A. This is the scaled value in a range of A to B. Okay, if you're not convinced, let's see. This is how you can scale any data. Okay, let's see how. Which value do you want to scale? Which value do you want to scale? Shall I go with 1 first?
Yes, sir.
Okay, let's see this. What is A right now? Minus 10. What is B minus A? 30. What was this value for 1? You computed this last value, right? What was this value for 1? This squishes the value in between 0 to 1.
0.
0. So if this is 0, what do you get? Minus 10. And this is what you want, right?
Sir, is it minus 10 into or plus?
In what case?
The values you have written, but in the formula you have written A plus B minus
A plus B minus A.
So, but when
So
you
B
are
is
actually,
B is your 20. A is your minus 10. So minus of minus 10 will become what? Plus 10.
plus, yes.
So
30,
that will be
but
30.
before 30.
Oh, sorry,
it is-
sorry. Thank you. Okay, thank you. All right. So this is now minus 10. Is this clear?
Yes, sir.
Okay. Now let's do it for 5. Okay. So if you do it for 5, do you remember what was this component? The fraction for 5. What was this component? 1. See, this is minus 10 plus 30 into what? For 5, what was this value?
1.
1. Okay. Keep this 1 here. What do you get? Minus 10 plus 30, which is 20. And this is what you want, right?
Yes.
Okay. You can do it for any value. You will get the desired results. Okay. All the values will now be squished between minus 10 to 20. Okay. So is this clear? Shall I move forward? Any questions here? Is it becoming too mathematical? Trust me, this is nothing.
Can we do
Yes.
it for the another one value, like
Yeah, sure.
for 3?
Which value do you want? Okay.
Let's
3.
do it
So
for
this,
3.
okay, what do you think the middle value between minus 10 and 20 is?
Middle
What is the
value,
yeah, what is the middle value?
let's say 15. Be
5.
the middle. Okay, okay,
5.
sorry.
I mean, the distance would be 15, right? Okay, look at 3. The distance is what? 5 and 10.
Yeah,
15. 5 and minus 10 is 15. 5 and 20 is 15. You'll see it will come out as 5. Okay, let's see. Scale the value 3. So this would be minus 10 plus 30 into what was 3 originally? 0.5. So this is minus 10 plus half of 30, 15. 5. Do you see that now?
yeah.
Okay, makes sense?
Okay, okay. Yeah.
All right.
Yes.
Okay, so this concept, the very first concept, this is the first type of feature scaling. This concept is called as normalization. Yeah. So normalization squishes the values in a range. Okay, it squishes the values in a fixed range. Okay, constrains the value in a fixed range, or you can say manually specified range. All right. Okay, I'm going to show you one more. This is an alternate form of scaling. This is called as standardization. Has this been discussed probably by someone before? Because this term is quite common, standardization. Discussed by somebody? Does anyone remember?
Yes.
Did you? It has been discussed, right?
I
No?
think it's been discussed.
Okay, it has been discussed. Okay, great then. And I'll just give you a quick recap. So the idea is, given a feature, okay, given a feature, what standardization does is it constrains, okay. Okay, what is the mean right now of your data? What is the mean right now of your data? And you don't even have to compute it, by the way, you can just tell me. What is the mean right now? 3. Okay. And what is the standard deviation? Standard
1.
deviation.
1.
No, it's not 1. Okay, standard deviation will be coming out to be something. So standard deviation is given as 1 minus of the mean. I mean, you are doing it for every sample, squaring it up. So this is the square of the square. This is the square root of the average deviation from the mean. 2 minus 3 whole square plus 3 minus 3 whole square plus 4 minus 3 whole square plus 5 minus 3 whole square. Okay, this is, I mean, if you divide this by 5, the number of samples, this is your variance, and then you take the square root of it. This is called as the standard deviation. You know that, right? Standard deviation is nothing but square root of your variance. And what is variance? It is the average square deviation from the mean. These things have been discussed before, right? These are simple metrics.
Yes, sir. These were all
Okay.
discussed.
These have been discussed before, right? Okay. So what is this number? Can you compute this? So this would be 1 by 5 into taking the square root. This is 4, 1, 0, 1, 4. So this is 10. 1 by 5 into 10 square root. So this is root 2. So standard deviation comes out to be root 2. Okay. So mean is this, standard deviation is root 2 currently. Okay. It will be different for different features. Okay. What we have to do when you are doing standardization, you have to ensure that, okay, you have to ensure that the, I mean, for the scaled feature, okay, the updated mean is 0, which means you are making it 0-centric. The new features should be in such a way so that updated mean is 0. You have to modify this. Okay. Let me call it standardized values. Okay. Standardized values. So you have to modify these values in such a way such that, okay, such that the mean becomes a 0 and standard deviation becomes a 1. For every feature, you'll be doing this. Have you done this before? Yes, people, have you done this before?
No, not really.
Yes.
You have done this, right? So what is the formula for it? How do you standardize a value? How do you standardize a value? Please note that STD is the standard deviation. This is not standardization. Okay, this is standard deviation. Okay, how do you do standardization? I mean, how do you standardize a value? Standardize. Anybody remembers? No? Okay. Subtract the mean and divide by the standard deviation. Okay. So you want to do it for what value? Tell me. Out of the 5 values that are given to you, you want to do it for what value?
3.
Okay, let's do it for 3. So 3 and the mean is what? You are saying that your value is 3. What is the mean? We computed this mean also, right? Mean is also 3.
3. 3.
So 3 minus 3 divided by root 2 comes out to be 0. Okay. All right. What will happen if you have the value as 1? If I take the value as 1, what will be the answer?
Minus 2 by root 2.
Minus root 2. Okay. This would be minus 1 by root 2. This would be 1 by root 2, and this would be root 2. Okay. You can compute all these values if you wish to. Minus 2 by root 2 will be minus root 2. Okay. So, okay, look at all these values. If I sum them up and divide by 5, what do I get? What is the resultant value? What is the resultant mean? If you look at these 5 values, if I ask you to compute the mean, what do you get? What is the updated mean? Can you compute it?
0.
Isn't it 0? Okay.
Yeah.
Compute the standard deviation, it will come out as 1. Okay. Compute the updated standard deviation, it will come out as 1. Okay. That's what the purpose of standardization is. Now we'll see why we are doing it and how it achieves. So do you realize that now, if I do it like this, do you realize that, okay, it is not necessary that it is going to squish every feature in the same range? Yes or no? Do you
Yeah.
realize that, I mean, it is not going to do that between say minus 5 to 5. In this case, it is minus root 2 root 2. Maybe one feature is still minus infinity to 1 or minus infinity to 5. Okay, it is not doing that. But let me tell you, it does it. How? Let's see that. Okay. For most feature values, you will see they will be between minus 3 to 3. If you remember Gaussian distribution. Okay. If you don't, then you'll not be able to catch up to this. Okay, let's see this. I'm going to make the bell curve. Okay. See, my drawing is bad, but I hope you get the point. Okay. So this is, say, your bell curve. Okay. What does this bell curve indicate? Okay. At what value do you have the peak?
Mean.
Mean. Okay. What does this curve indicate? So these are essentially the feature values. Okay. The x-axis is nothing but the feature values. This axis is what I'm plotting. Okay. These are the feature values. These are the feature values. See, your feature values currently are how many? 5, right? So one of the feature values is I'm talking about the standardized values. Okay. Let's say one of the feature values minus root 2. So minus root 2, what is the mean right now? Updated mean.
0.
0. Minus root 2 will be towards the left, right? Yes or no?
Yes.
Same thing.
Yes.
I mean, positive root 2 will be towards the right. 1 by root 2 will be somewhere here. Okay. Minus 1 by root 2 will be somewhere here. Okay. I hope you get the point. So these are the feature values that you're plotting on the x-axis. See, many people just cram what bell curve. I mean, this is bell curve. What is bell curve? Can anyone tell me? What is bell curve? What is this curve representing? Probability of what?
Probability distribution
Of what?
of like these features
Feature
inside
values.
features.
Probability distribution of these feature values. So what you are saying is, okay, let's try to interpret this. What you are saying is, what is the chance that if I give you, let's say, a big data set, okay? If I give you a big data set, what is the chance that 0 can be selected from that data? What is the chance? 0 can be selected from that data. What is the chance? Let's say if this value is -3. So you will say that what is the chance that -3 will be selected from this data? Is this part clear? If I ask you, what is the chance that 5 is selected from this data, or somebody can have a value 5? See, currently, if we are trying to determine, say, the features about somebody, if this feature was, let's say, age, I have 5 samples, right? Where do you think I will collect these 5 samples from? When you make a data set, you will go to a community and you will select 5 samples from it, right? Will you, go to more than 5 people if your purpose is just to take 5? Think about it. If your objective is to just collect data from 5 people, would you go to more than 5 people?
No.
No, right? So what if you went to some other 5 people? Don't you think the data would change?
Yes.
Yes.
I hope you get the point. So the idea is, see, you may want to know what is the chance that if I would have visited some other people, what is the probability that I will see that value? So you collected your data from a fixed number of samples, right? So I'm just asking, what is the chance that if you visited that community again and looked for, say, another 10 random people, if so, look for another 5 people, what is the chance that you will see that value, say, -3? This indicates you will see what is the probability that you will see a value 5. That is what this bell curve indicates. Okay. Now, in essence, in simple words, this bell curve is nothing but, in mathematical terms, it is called as a probability density function, the PDF. Okay. This is indicative of the probability for the feature value xi, okay, to have some value. This is the value that you will observe. Okay, this is the value that you will observe. Given what? See, you are currently assuming something, right? Bell curve,
Standard
mean and standard deviation. What is the mean right now?
0.
0, and standard deviation is
1.
1. So given this mean and standard deviation, so if you assume mean and standard deviation, what distribution are you assuming?
Normal distribution.
You are assuming normal distribution. And that's what you have studied before, right? This is also called as Gaussian. So you are assuming that your features are normally distributed. Okay. And then you are trying to compute this probability value, okay, for a given, for a given number. Okay. This is given as, so for different distributions, this PDF is different. For normal distribution, I don't know if you remember or not, this is 1 by √2 pi sigma. Sigma is the standard deviation. Okay, I'll just mention it here as well. This is also represented as sigma. Okay. Okay, this is your standard deviation, by the way. Okay, pi is the symbol, right? 22 by 7. So e to the power of minus of this val minus mean whole square divided by 2 sigma square. Sigma square is your variance. Have you seen this formula before? Yes, people. Have you seen this formula before?
Yes.
You must have, right? I think this would have been discussed by your previous mentor.
Yes.
That is what the value is. You substitute mean as 0, standard deviation as 1. Whatever value that you get, that is the probability for it. Now, can you tell me what is the area under the curve? What is the area under this whole curve? It's a probability density function. Anybody who remembers? Okay, if you sum up all the probabilities, what does it sum up to?
1.
1. Here also it will be summing up to 1. It's a continuous distribution. It's not a discrete distribution, it's a continuous one, right? You can do it for any feature value, right? So if you sum up all these probabilities, it will sum up to 1. Okay, keep this in mind. Okay. Okay, the area under the curve for any probability distribution is a 1. Okay. Now let me see how much you are able to recall about normal distribution. Okay, I think other instructors would have taught you this. When you look at within one standard deviation, so I'm going for mu plus sigma and mu minus sigma. What would be mu plus sigma value? What is the mu plus sigma value? What is this value? Mu is 0, sigma is 1. So this would be 1 and this would be -1. Okay. So can you tell me how much percentage of data is held between -1 to 1? If you assume normal distribution,
68, 63.
around 68%. Okay, around 68 point something percent, 68.5 or 68.4, something like that. Okay, so within one standard deviation, do you think it is guaranteed? No. Okay, but what this means is that if you look at a feature, if you look at its values that you have collected, if the data is actually normally distributed, this number would be very, very close to it. Okay, now what happens between two standard deviations?
95%.
95%. So most of you remember, so between -2 to 2, this is 95%. Okay, within this range, it is 95%. And within 3 standard deviations,
97.
99.7% actually. All of it almost. Okay. Okay. Can you tell me for our data set, when we standardized, how many values are present between, say, -2 to 2? Look at the values that I did for you. How many values are present between, say, minus? Okay, let's talk about -1 to 1. How many values are there between -1 to 1? Within one standard deviation, out of the 5 values that you are having, okay, how many values are there between -1 to 1? 3 values. So what is the percentage? 60%. Do you see that it holds it almost even with 5 samples? Okay. What percentage of the data is between -2 to 2?
100%.
100%. So now you have to realize this. Okay. When you are standardizing, can I say that it is almost guaranteed that the majority of the data would be between -3 to 3? Yes or no? For the given example, it is actually between -√2 to √2, -1.414 to 1.414, all 100% of it. So can I say that in the worst case, most of the data would be between -3 to 3? Yes or no?
Yes.
Does it make
Yeah,
sense?
we can
Okay.
say, yeah.
Okay. So it is not guaranteed to be in it, but I'm saying the majority of it will certainly be there. Okay. And this holds true. I shouldn't say it's a fact, but this is true for most features that you will collect or that you will see in any data set. Okay. True for most features that you will ever see in your data set. Okay. Unless they are synthetically generated using a specific distribution. So normal distribution assumption, this assumption is a very valid assumption. And you can assume this when you have even more than 20 samples. It's a really good assumption to make. Even when you have 20 samples or more, you can do this assumption. And see, it holds well for 5 examples also. That's what I was trying to convey. But in general, if you have more than 20 examples, it is a valid assumption to make. Okay, it is a good assumption to make. So most of the values that you will see when you standardize in your data would be between -3 to 3. Can you tell me if a value is, say, beyond 3 or beyond -3, what would you call it?
Outlier.
An outlier or an anomaly. So using this method, people can actually find outliers also. So I'm going to just change the formula. So any value that you are given, I'm going to standardize it. I'm going to subtract the mean and divide by the standard deviation. And after this, I will take the magnitude. Okay. So if it is greater than some threshold, I will say it's an outlier. Okay. Else not an outlier. So what should be the threshold?
That should be
3.
3. Okay. I mean, closer to 3. Okay. See, if you want to be a little harsh, go with, say, 2.75. If you want to be more harsh, maybe say 2.5. Okay. So the worst that I have seen is 2.25. Okay. If you want to eliminate more and more samples. Okay. You see, is there a way that I can, for sure say with certainty that a point is an outlier or not? Do I have that proof? No, right? It is an, you can say it is a way of doing it. It is a heuristic. Okay. I don't have a proof, but if I want to eliminate some outliers, this is how I can do it. This formula is called as Z-score. It's called as Z-score for any value. It is the standardized absolute. Okay. Okay. It is the absolute of the standardized value. All right. This is one popular metric to remove outliers. Okay, you can do outlier detection with this. So standardization is another way of scaling. And standardization is actually more useful when you use linear models. We will talk about linear models in the next class tomorrow. So you will see standardization is pretty useful there. Okay. Normalization you can do over there as well, but standardization achieves slightly better results in most cases. Otherwise, they are both good. Okay. Otherwise, they are both good. Okay. So in k nearest neighbors, you prefer normalization. In linear models that we will discuss soon, you will prefer standardization. Okay. Because those models make an assumption that your errors are normally distributed. Okay. And because you are making that assumption, it is better to use standardization. All right. If you didn't understand any of the things that I said, forget about it. Okay. I'll tell you what to remember when we discuss linear models. Okay. So far we have seen different distance metrics. We have seen different evaluation metrics. We will see one more thing, how to aggregate, how to unify the predictions. Okay, how to unify the predictions. How to unify the predictions. So imagine I'm doing more than one neighbors. So let's say I'm doing 3 neighbors. Okay, so I'm doing 3 nearest neighbors. Okay, I look at a sample. So this is, I have a test sample. Okay, and for this test sample, I find the 3 closest neighbors. Okay, so this is, say, the closest neighbor. Okay, maybe say this is the second closest. So with respect to the closest, second closest, and the third closest, okay, I have their output values. Okay, I have their output values. These are the y values for these closest neighbors. Let's say this is 10, 20, and 30. Okay, and see, once I'm computing the distance, let's assume I'm using Manhattan distance. Okay, my distance is Manhattan. Okay, the distance was maybe say 2, 3, and 4. Okay, my question is this: how would you unify the predictions when you have 3 closest neighbors? What would you predict? What should be your prediction for this test sample? You have been given the output of the 3 closest neighbors, the mean, right? The average. That is one way to do it. Okay, is it a good way to do it? That's a question. Okay, I'll rather pose it as another question. Do you think when you are computing the average of the outputs, are you considering the distance? Are you giving weight to the closest samples, more weightage to the closest samples, and less weightage to the second closest, and even lesser weightage to the third closest? Are you doing that when you are computing the simple average?
No.
No, right? So when you simply compute the mean, okay, when you simply compute the mean, just give me a second, please. Sorry for the inconvenience, people. Am I audible now?
Yes, sir.
Yeah.
Actually, there was a call from a courier person. So he's standing downstairs. I've asked my wife to collect it. Okay. All right. The average, actually, if you see this, okay, the average that you're computing for the predictions, this is computed like this, right? You take 10, the first prediction. Let's call this prediction. This is the actual value. This is the second actual. This is the third actual. So you're essentially doing this: y1 plus y2 plus y3. Okay, and then you're dividing it by 3. This is what you do, right? The number of samples. That's how you take the average. Let's try to focus on this. I will try to write it in this way, okay, which is the equivalent way of, I mean, it's the same way that I'm doing. But now I've just taken this 1 by 3 out and multiplied it with every quantity. Do you see that the weight is the same for every output? Yes or no?
Yes.
Can I say that this is the weight, right, that is associated with the prediction? And it is the same for everything. So when you are taking the average, you are assuming equal weight for every sample. Okay. So if there are k neighbors, what would be the weight for every sample?
1 by k.
1 by k. Okay. All right. So can you comment about the weights? So what should be the weight in general? It should be greater than 0. And what should be the sum of weights?
Sum of weights is 1.
1. Okay, keep this in mind. Okay, this is important. Okay, so these two properties should hold. Okay, these two properties should hold. Okay, all right. So I'm going to show you a weighted way of averaging where you use the distance. Okay, so if you look at the distance, okay, for the closest sample, it is the lesser. That's why you are saying it is the closest. For the second closest, it is the second least. And the third closest is basically the third. I mean, I should say the third highest. Okay, because it's distance. So what should be the weight? It should be inversely proportional to the distance or directly proportional to the distance. If you want to give more weightage to the closer person,
Inversely proportional.
inversely proportional, right? We want to give more weightage to the closer sample. Okay, so these weights have to be inversely proportional. Okay, to the distance. To the distance of the ith sample from the query point, from the test point. Yeah. All right. So if I directly take the distance, okay, if I directly take the distance, so what is my weight of sample 1? Look at the numbers. What is the weight of sample 1? The closest neighbor? 1 by 2. The next one would be 1 by 3, and the next one would be 1 by 4. Is the sum equal to 1?
No.
Or is it guaranteed that it will be equal to 1 ever? No, right? It depends on the number of neighbors, right? And what is the distance between them? So we have to ensure that their weight sums up to 1. So what should we do? Modify these weights such that their weights should sum up to 1. What would you do? Scale these values such that their sum is equal to 1. What would you do? Change 1 by 2 to some value, change 1 by 3 to some value, and change 1 by 4 to some value. So their sum is equal to 1. You have to change this value 1 by 2 to something, 1 by 3 to something, 1 by 4 to something, so that their sum is equal to 1. That is what you have to do. What would you do? Maths question, nothing special. Okay, let me show you how to do that. So use any weight, okay? Okay, use any weight. It is 1 by distance. But what you are going to do is you are going to divide it by the sum of the weights. Okay, you are going to divide it by the sum of the weights. Okay, you're going to divide it by the sum of the weights. Okay, is this part clear? You're going to divide it by the sum of the weights. You can simply say it like this. Okay, let's call this as wi. So updated wi would be this. Okay, updated wi would be this. So if you do for this 1 by 2, divide by for everything. 1 by 3 would be 1 by 3 divided by 1 by 2 plus 1 by 3 plus 1 by 4. Do you realize that if I do this, the updated sum will be equal to 1? Yes or no?
Yes.
If you add these three quantities again, don't you
Yes.
think that the sum will be equal to 1? It will be, right? Okay. So you have to scale the values such that the sum is equal to 1. This is another form of scaling, by the way. Yeah, this is another form of scaling. But our purpose here is that like the sum should be equal to 1. Okay. So you do this, and whatever weights that you get, okay. So whatever weights that you get, multiply W1 with 20, W2 with 30, and W3 with 40. And this should be your weighted prediction. Okay? It's also called as weighted aggregation. Okay? This is weighted prediction by distances. Okay, weighted by distances. All right. Is this clear? This was the output for sample 1. This was the output for sample 2. This was the output for sample 3. Okay. Now you have computed the weights from the distance. Okay. All right. So this is weighted aggregation. You will see that in k nearest neighbors also. Okay. It provides you both ways. By default, it does averaging, but there is an argument that you can specify that can be used for, weighted averaging as well. You can call it weighted averaging also. Yeah. It's called as weighted averaging. Okay. So, okay, I believe this is more than sufficient for the theory part. Let's discuss, okay, how to do it for multivariate data. Okay. Let's implement all these things. See, I have a request. Whenever you are coming for any of my sessions, please revise at least the last session. Okay, because all the things are connected. It'll be easier for you to follow. Okay. Okay, so let's import the basic libraries. Okay, let's take a small data set. So there in scikit-learn, the library for machine learning, there are some small data sets that are available that you can use. Okay, so you can, I'll just paste this link for you guys. Okay, so these are some of the data sets that are available. Okay, these are real data sets, but you can say a subset of the actual data sets. So I want to use a regression data set. Which data set do you want me to use? So there is this one, which is diabetes 1. So given some features, we want to know how much the impact of diabetes has been on the health of an individual. The output indicates higher the number, more is the impact. So this is one of the data sets. This is another, which is an exercise data set. This is also a regression data set. Okay, so people are doing some exercises, and then you have to predict probably something related to the exercises. Okay, I don't remember much. Like which of these two data sets do you want me to pick? There are two only in this.
Let's take diabetes.
Okay, let's go with this one, diabetes data set. Okay. So if you want to import this, go to this sklearn.datasets. Okay, and you have to import the name of this data set. Okay, I'm just going to show you how to work with this. So you have to instantiate this object of load diabetes. Okay. Now, did I discuss such type of data sets in the last class? Did we see any of these data sets in the last class?
No, sir.
No.
Oh, okay. All right. So if you want to see the type of this data set, this is something that you would not have seen before. This is called as a utilities bunch file. Okay, it's a special file called as bunch. Now the name itself tells you that bunch, in English, it means it's a collection of multiple things, right? Bunch means a collection of multiple things. So this bunch file is also a collection of different things. Okay, and what are the different things? Let me just show you. Okay, so there are two ways to access what are the entities in this bunch. So one is you use this command dir and you look at the data set, and it will show you what all available items are there in this bunch. So these are the available items. Okay. Another way to look at this is there is this feature which is called as keys. Okay, just like your dictionary keys. Okay, and it shows you the same thing. Okay, this is how you can access the items in a bunch. All right. Now, what are these items? You don't need to know about all of them, but I'll show you the. So DESCR is the description, data is the features, okay, and target is the output, and feature names is the names of the features. Okay, you will use only these four: target, feature names, data, and description. You don't need to use anything else. These are the items that I require, okay, that you will require as well. So let's see the description of this data set first. So you can access a description of this data set using, so this is like an object. Okay, so how do you access an object? What operator do you use? If you have done Python, if you have worked on Python classes, how do you access an object of a class? An attribute of an object? Which operator? Dot operator. Okay, so you will use this description. Okay, so the first one is a description. So I'm going to show you the description of this data set. Okay, look at this. It is kind of not readable, right? I mean, which character do you see is properly, improperly formatted, which is not correctly formatted? There is one character, /n. So if you want to format this special character, you can use the print command, because print format /n. Okay, look at this. This is now easily readable. So it says it's a diabetes data set. There are these 10 features: age, sex, BMI, average blood pressure, and there are 6 blood serum measurements. So different types of readings have been taken from the blood. Okay, there are a total of 442 samples. So 442 patients, 10 features. These are the features. Okay, these are your features: age, sex, BMI, BP, and these are 6 serum measurements, blood serum measurements: total cholesterol, low density lipoproteins, high density lipoproteins, and so on. Okay. So I want to know where the data is. Okay, so you can get access to the data using this property called as dot data. Okay? This is the data property which is going to give us the features. So I'll save it into X. So can somebody tell me what should be the shape of this X? These will be the feature set, the inputs. Okay, what should be the shape of the input? If you remember, what should be the shape of the input to any machine learning algorithm? When you fit the model, what do you provide in the input? Number of samples times number of features. Okay. So what would be the shape of this? Look at the number of samples and number of features. 442 times 10. Okay. So this is your 442 times 10. Why is your output? It is present in the property called as target. Okay. It is present in the property called as target. Okay. So you can save it like this: target. Okay. This is your output. Okay. This will be number of samples, comma. Okay. If you look at this, this will be simply number of samples. So this is 442, comma. Okay. Is this clear? Yes, people. Is this clear?
Yeah.
Okay. So now what I'm going to do is I'm going to split this data set into 2 parts: training and testing. You have seen this before already. So let's split the data into 2 parts. Go to sklearn model selection. Okay, and split your data into 2 parts with the help of this function called as train test split. This function can be used to split your data into 2 parts: training and testing. Okay, what it needs is the data X and Y. It needs you to specify the size of the test set. How much data out of 442, what percentage of it do you want to go to the test? What percentage of 442 do you want to go to the test?
30%.
Okay, let's go with 30. I couldn't hear you, sorry. I heard someone saying 30. Okay, so 30%. And there is this argument called as random state. Let me show you without random state what happens. Okay, so this will give you 4 components: xtrain, xtest, ytrain, and ytest. So basically it is splitting the training features, the train input, the train output, the test input, the test output. Okay, let's see this. So the 70% of 442, whatever that number is, that is going to training. You can see 309 samples in training and the remaining in testing. Okay. My question is this. Let's look at this X train. Okay, let's look at this X train. So what this function does is it shuffles the data and then splits. Okay. So if you look at the first two samples, okay, I'll just show you the first two samples just in case. Okay, let's look at the first two samples. Okay. I'm going to run it again. What do you think will happen? Will it change the data set? Will it change X train and X test? The number of samples will stay the same, but what about the order of the samples? Will it be the same?
It may
It will
change.
change.
It will change, right? Because
Yeah.
what this function does, it randomly shuffles the data and then splits it. Okay. So if you see this now, let's just compare it. Okay, let's just compare it. Do you see, are the values same? Look at the first two samples. I copied the first two samples just
No.
for demonstrating.
No.
Okay, no, right? So if you want to get the same results, okay, see, when you're evaluating your models, your data set in the train and the test has to be the same when you're making comparison with somebody else. So whatever data set I am using, you should also use the same data set if you want to compare my model against yours. Okay, you cannot say that I'm using an algorithm A, but the data set is different. So that is not a fair comparison. Okay, so this is this argument called as random state. If you and I keep the same integer, we will get the same data set. So let's see this. Okay, let's see this now. Okay, just remember this first example. Okay, first two values 0.0303 and minus 0.044. Okay, I'm going to run it again. You can see that this number will change. So this is now 22, 23, 24, and let's see that again. Did you see the data set did not change? I'll run it one more time if you're not convinced. Okay, data set will not change now because random state tells it shuffles the data in a specific way. By default, this random state is your system clock, which always keeps on increasing. Okay, so that is why when you run it without the random state, you get different results. Okay, so keep this random state. Yes. Any questions? Yes, people. Any questions as such?
No.
Good.
Okay.
sir.
Random state can have any value from.
Yes, as long as you and I have put the same integer. It takes in integers only.
Okay.
Okay. It can be a negative integer also. As long as you and I keep the same integer, our data set would be the same. Okay. All right. Okay. I mean, if you put a different random state, our
So-
data sets will be different.
Okay, so this is not that I need to put 0 and 1 like to say
Any
it's
number.
false and true. Okay.
Let's say I put 100. See, the data set would change if you want to keep the same data set in your training set. Keep random state as 100. Okay, any integer would do. All right, so we have split our data. Okay, this is my train set. I just wanted to see. I'm going to show you the minimum and maximum values. By the way, these are your feature names. Okay, so there's a property called as feature names, and this is how you can, access it. Okay, the feature names. I'm going to put everything into a data frame because I believe it's easier to visualize everything in the form of a data frame, right? It's nicely formatted and everything. So data is in X. My column names are this dataset dot feature names. Okay, so this is the data which is nicely formatted. You can see that. Okay, let's save it into this DF, and I'll show you the first few values just for your understanding sake. Okay, I want to show you a few things. So maybe let's say the minimum and maximum values. So you can use this describe to get the descriptive statistics. So these are your descriptive stats. You see minimum and maximum. I want to only extract minimum and maximum. Okay, let me do this. Let me take the transpose of this matrix so that I see features on the left hand side and minimum and maximum on the on the horizontal side. Okay, what I will do now is I am only interested in minimum and maximum, so I get only minimum and maximum. This is how you access a data frame. Okay, I want you to comment on it. Are these minimum maximum values in the same range, or are they different? Is the range of every feature the same or different?
Different.
Very different, right? So we should scale our data. That's one thing. Okay, so feature scaling is required. So I'm going to show you how to do feature scaling. Let's do normalization. To normalize your data, what you should do is go to sklearn. Okay, there is this library called as pre-processing, because normalization is a pre-processing step. And the name of the function is min max scaler. It uses minimum and maximum, right? Okay. So this is called as normalization. So let's take this min max scaler. If you want to provide any feature range, you can do that. Okay, which feature range do you want? Which feature range do you want? Yes, people. Which range? Give me any range.
0 to 1.
See, if you want to say 0 to 1, you can do 0 to 1 also. By default, if you want to do it in 0 to 1, you don't even have to specify. Okay, I'll show you. You don't even have to specify. Okay, so I'm going to fit my data on Xtrain. Okay, so this will compute the minimum and maximum from every feature. Okay, and now you will be transforming the data. So you have transformed the data of training, and let me store it in transformed Xtrain. So this transformed data will now be scaled between 0 to 1. Same way, I'll transform the test set also using the same scalar, using the same min and max from the test set. Okay. Sorry, using the same min and max from the training set. Okay. Let me show you that the transform data, okay, is now between 0 to 1. Okay. Let's put this transform data with the columns. Okay. Okay, so this is your data frame right now. Okay, you may not see, okay, it has, though the values have changed, you can see that some values are negative, and now the values are what we say is, I mean, between 0 to 1. It may not appear to be that way, but let's see. Okay, let's see. So what we'll do is, I mean, let's use a describe function on it. Okay, and now I'm going to take the transpose, get the min max. Okay. Okay, do you see that now everything has been scaled between 0 to 1 in the transformed set? Is this clear? So when you want to scale it in any range, right, provide the feature range like this. Okay, provide the feature range like this. Let's say I want to do it in -5 to 5. Okay, so provide it like this. So you have to call this feature range and provide this as -5 to 5. Default value is 0 to 1. Okay, default range is 0 to 1. I'll show you. Default range is 0 to 1. That's what I did, right? I did not specify any argument. Okay, now I'm going to do it in -5 to 5. Let's see. Do you see that now it has been scaled between -5 to 5? All the features. Let me show you the data just in case if you are concerned. Okay, all the values are now between -5 to 5. You can see that all values are now between -5 to 5. At least the ones which are displayed here. All right. So now that I have scaled my data, I can use k-nearest neighbors. So I'm going to use k-nearest neighbors from this library called as neighbors. And the name of the function is k-neighbors regressor. Okay. So this is your model. Use this k-neighbors regressor. How many neighbors do you want? How many neighbors do you want? Give me a number.
3.
3. Okay. If you want to use any distance metric, this is called as metric. Which distance metric do you want to use? By default, this value is actually Minkowski. Okay, with p equal to 2. By default, this is the value. Okay, with p equal to 2. Okay. So which one do you want me to use? You can specify anything here, Euclidean, Manhattan, like any type of similarity metric that you, distance metric that you want to have here.
We'll go with Manhattan.
Okay, let's go with Manhattan then. Okay, you can simply say Manhattan, or you can set the p value to 1. Okay, you can do this or simply put the value of p to be 1. Okay, so this is your Manhattan right now. And we want to do what type? Averaging type. What is it that you want to do? Simple averaging, basically the mean, or weighted averaging? Tell me.
Weighted averaging.
Weighted averaging is called as distance here. And if you want to do simple averaging is uniform. It gives uniform weights. It gives uniform weights. Okay. So specify your weights as uniform. By default, this value is uniform. Okay. See, if you're not convinced, let me show you the documentation. This is the documentation. Okay. You can always check the documentation for the default parameters. The number of default parameters are 5. Weights, as you can see, is uniform, which means you're doing simple averaging. Okay. Algorithm, you don't need to worry about. See, we are using the concept of finding the nearest neighbors, right? This algorithm figures out how to find the nearest neighbors. There are many ways to find the nearest neighbors, not just the brute force way. So automatically selects what is the best way for you. Okay. I'm not sure how much of how many of you know. Have you heard of these data structures like KD tree, ball tree? Have you heard of these data structures?
No.
Okay, so if you don't know about them, just skip those details. Okay, the idea is internally what this function does, it uses these data structures to compute the nearest neighbors, to find the nearest neighbors quickly instead of brute forcing through every sample. Okay, so I mean it intelligently figures out, you can say efficiently figures out the distance between the neighbors using some data structure. It is not just that every sample is stored in a matrix and it is computing that. No, that's not how it does it internally. Okay, you can see p value is 2, metric is Minkowski. If you want to change some parameters, you can do it in metric params, and this is an important parameter that you will be using when you join a company. Maybe not right now, but let's say if you have a big data set, you can specify this number to -1, or you can specify it to positive integers. So let me tell you what this njobs does. See, when you're working on a machine, you have a processor, right? You have a computer CPU. So can you tell me the name of your CPU right now? Some of you, which processor are you using in your system? It would be written like Intel i3, i5, i7, something like that. If you're using Mac, it would be some M1, M2, M3, something like this. Which processor are you
I
using?
think I'm using i3.
Okay, so if you use which generation do you remember?
I think Gen
8th, 9th, 10th, 11th.
I'm not sure about that.
Okay, anyways, so see, each of these processors, they have multiple compute units. They are called as cores. And there are multiple cores in a processor. Okay, so if you use this number as 1, it will use only one core. None means only the first one. Okay, it means 1. If you say 2, it will use 2 cores. If you say 3, it will use 3 cores. If you say 4, it will use 4 cores. If you have 8 cores, you can go up to 8. If you directly want to say -1 means all the cores. So you can use njobs as -1. It is not advisable to use it for small data sets, because if you're doing it for smaller data sets, it takes actually more time because the data has to be split into multiple cores. And then each core figures out the nearest neighbors quickly. Okay, for bigger data sets, you will see a speed up. For smaller data sets, you may not. Okay, so I don't advise it for a small data set, but for bigger data sets, you can set this number to the number of cores that you want to utilize. -1 indicates all the cores. Okay.
So can I say this njobs is like to achieve parallel processing?
Parallelism. Yeah, and this is there to achieve parallelism. Okay. See, because you can think of it like this. Many individuals are computing the distance now instead of 1. Okay, that will help you. I mean, quicken the process, right? Okay, so I'm going to fit my data onto my transformed set. So provide the inputs and the outputs. If you remember, to the fit function, you provide the inputs and the outputs. Okay. And now, once this model is trained, you can use this model for making prediction. What method do I use for predicting?
Predict.
Predict. So you can get the prediction for all the test samples. Okay, these are all your predictions for the test samples. Okay, so let's call this as spreads. Okay. Now my question is this: I want to compute some mechanism, right? Like how do I evaluate how well I'm doing on the test set with 3 neighbors, Manhattan distance, and the weighted averaging? So can you tell me which metric do you want me to use? Like one specific metric?
Maybe R2 score or.
Okay, let's use R2 score. And maybe you want to say something else. I'll show you how to do that as well. Anything else that comes to mind? Sum of squared errors, mean squared error, anything. So you have to pass the actual values and the predicted values. Okay, so these are the actual values in y-test. Predicted values are, I've stored it in preds. So this is the R2 score right now. Decent model, not a very good model, but a decent model with 3 neighbors. Okay. If you want to use maybe say something else, say for example, I want to use mean squared error. Okay. So you can use mean squared error. Okay, and you can simply say mean squared error and pass the actual values and the predicted values. So this is the mean squared error. Okay. If you want to get sum of squared errors, there is no function as such, but multiply this with the number of samples. And number of samples are here in this y-test dot shape of 0. This will be the number of samples in the test set. So this, so this is your sum of squared errors. This is your sum of squared errors. Okay. So you can use mean absolute, sum of absolute, whatever you want. These are the metrics that are available that you can check out. So go to the left-hand side. These are regression metrics. Did I show you these metrics the last time? Did we see these metrics the last time? This is the R2 score. Okay. The first one, the formula that we discussed today. Okay. We have mean absolute. Did I show you these metrics last time?
We have seen about the
This web page I showed you, right? Last time also.
yeah,
Or not?
page, yeah, that documentation we have gone through. Yeah.
Okay. All right. All right. Okay. All right. So I know the R2 score for this 3 neighbors and Manhattan distance and weights is this. So I want to know, okay, for different neighbors, okay, what is the result? Okay, for different neighbors, what is the result? Okay. Before that, I'll pose a question here. So I have split my data and okay, let me make one more comparison. Let's do it with this. Okay, let me make one more comparison. Okay. So this time I'm going with 2 neighbors. Okay, this time I'm going with 2 neighbors. Okay, and I'm computing the R2 score. Okay. So I fit the model. Predictions can be obtained from model.predict. Okay, on your test set. So which one is better? Look at the R2 score for 2 nearest neighbors and 3 nearest neighbors.
2 nearest will be better.
Look at this carefully.
Higher the value, so
Higher value, right? So 3 nearest neighbor is better, right? This is with 3 nearest neighbors, 0.3471. Okay. So R2 score tells me, okay, higher the better. Now my question is simply this. See, I am evaluating the model on a train test split, right? I split the data into train and test, and the model is evaluated on the test set. Do you think that if I would have shuffled my data in a different way, then probably 2 nearest neighbors would have been better? Is it possible?
How so?
Why not? I mean, is it guaranteed that 3 nearest neighbors will always be better for any type of split that I do?
No.
Not guaranteed, right? I mean, we are just making a claim on one split that I did. Okay. So if you want to be unbiased, okay, instead of doing a single train test split, the suggestion that I have for you is this. Okay. One way to do this experiment to achieve whether 2 nearest neighbors is better or 3 nearest neighbors is better, what you can do is you can divide the data maybe say 10 times. So let's say, so every fold is like, so I'm going to do this experiment 10 times. Okay. So every fold is indicative of how many times you are going to run this process. So let's say I'm going to run it say 10 times. So every time I'm going to split the data. Okay. Look at this carefully. Every time I'm going to split the data. So let's call it train 1 and test 1. So this is the first split. Okay. This is the first split. So you can say that my train and test sets have some samples. Okay. Similarly, the second time I'm going to run, I'm going to say train 2 and test 2. Okay. And similarly, I do it for the 10 times, and this would be train 10 and test 10. Okay. This is the, I mean, these are just the notations that I'm using, symbols I'm using to represent the train and test sets. My question is this: if I do this experiment now, and say on 6 out of these 10 folds, 6 out of these 10 times, maybe say 2 nearest neighbor is better. So will you agree with me that maybe say 2 nearest neighbor is a better way to choose it? I mean, 2 nearest neighbor is a better model. If out of these 10 times, 2 nearest neighbor was outperforming 3 nearest neighbor.
Yes.
Will you agree with me? I mean, does that make sense? Okay. So this is a much more unbiased way of evaluating. But the problem is, there is one more problem. Okay, there is one more problem. See, you're splitting the data randomly, right? You're splitting the data randomly. Okay. The other problem is, okay, I want you to focus on the intersection between the test sets. Let's look at any test set, let's say test I and test J. Is it guaranteed that these test sets will not be overlapping? You're looking at the intersection between them. Is it guaranteed that the intersection between test I and test set J, okay, will be, I mean, non-overlapping?
No, it might overlap.
They might overlap, right? So there is still some biasness. Why? Because see, train sets will definitely overlap because train sets are bigger, right, in comparison to test. If you do 80-20 split, 80% of data goes to train 1, 80% of data goes to train 2. So there is an intersection there for sure. But in test sets, it is not guaranteed, right? I mean, it can overlap, it may not. But we want it to, I mean, we want the guarantee that it shouldn't overlap. Okay. So there is one more way to do it. Let me show you how to do that, which is like even more unbiased way of evaluating. So that method is called as k-fold cross-validation. Okay, this method is called as k-fold cross-validation. Okay. So here you are not going to do random split. Please note this. Okay, this is not what you will do. Okay, I'll give an example and we'll show you what are the train and the test sets. Okay, assume that you have 100 samples in total. Okay, that you want to split into train and test. How many times you want to run this experiment? Tell me. You want to run it 10 times or 5 times? How many times you want to run this?
5.
Okay, let's say you want to run it 5. This K is for k-fold cross-validation. That K is for K nearest neighbors. Okay, don't use the same terms. I mean, don't get confused between the two. So this K here signifies the number of times you run this experiment. All right. So what you're going to do is you're going to divide your data into 5 parts. Okay, divide the 100 samples into 5 parts. Since you want to do it 5 times, so divide the data into this K parts. So what is your K? K is 5. All right. So what you're going to do now is the test set 1, okay, Can you tell me how many samples will be there in each part, in each partition? How many samples will be there in each partition?
20.
20. Spot on. Okay. So in the fold one, what you do is, let's say these 5 partitions are P1, P2, P3, P4, P5. Okay. Let's say these are the 5 partitions. Okay. If you have 10 partitions, then there will be P1, P2 up to P10. So in the first fold, test 1 is P1 and everything else is in train 1. Can you tell me how many samples are there in the train set right now?
Now it will be P2, P3, P4, P5.
So total how many samples?
80,
80. And how many are in testing?
20.
20.
20. Okay. In the next step, what you're going to do is use P2 to be your test set, and everything else will be the train set. Okay. So do you ever think there will be an intersection?
No.
No, right? So the idea is very, very simple. Okay. The idea is very, very simple. For the ith fold, the ith partition goes to testing and everything else goes to training. Okay. Everything else goes to training. So there is no intersection ever. This method is called as k-fold cross-validation. This is the method which people use to evaluate your models. So you run these train test splits multiple times, ensuring cross-validation. Okay, ensuring cross-validation. And then you evaluate which model is doing better. Okay. So I'll show you how to do this in the next class because we have limited time. Okay, we just have 3 minutes. If you want to discuss anything else, we can do it in the last 3-4 minutes. Tell me. We'll implement this in the next class. Yes, people. Anything comes to mind? Tell me.
Can you go over the full cross validation once again? If that's okay.
Yeah. So the idea is, we want to ensure that when we are comparing our model performance, we shouldn't do that on a single train test split. That would be a biased evaluation, because maybe the model that you say is better is only better for the test set that you chose. If I would have used any other test set, maybe that particular model would actually be worse than all of them, all of the other models. Okay. So we should evaluate your models on multiple test sets. That's what this means. So when we are doing this k-fold cross validation, what we do is, so if your data set has 100 samples, you divide the data set into say 5 parts if you are interested in doing 5-fold cross validation. Okay. If you say I am interested in doing 10-fold cross validation, so you will have 10 partitions in that case. So every time you are doing this, let's say you are doing it the first time. So you're going to break it into train and test. So the first time that you do, use the first partition in testing and the remaining partitions in training. Okay. In the second time, use the second partition in testing and all other partitions go to training. The third time, the third partition goes to testing and everything else goes to training. So this ensures that there is no overlap in the test sets and you can evaluate your models in a better unbiased manner. Now I have a question. Okay. Please listen to this very, very carefully. And with this, I'll end. For getting, let's say, the best unbiased evaluation, okay, what should be the number of folds? What should be the number of partitions? It should be high or low. If you want to evaluate it in a super unbiased manner, it should be high or low. Think about it. If you want to actually figure out, okay, which is better, 2 nearest neighbors or 3 nearest neighbors, don't you want to evaluate it in many, many times? Yes or no? If you want to truly get the result, okay, if 2 nearest neighbors is better or 3 nearest neighbors is better, right? So what is the highest value of k possible? For this data set, what is the highest value of k possible? Think about it. 100. Okay. So in that case, you will be doing 100 100-fold cross validation. So how many samples will go to the test set in that case?
For test, it will be
One.
One only. One only. Okay. That would be very, very expensive if you think about it, right? Because you're going to do this 100 times. Okay. So please note that. that one has a special name. If your k is equal to the number of samples, okay, if your k is equal to the number of samples, okay, that one has a special name. We don't use it, okay, we don't use it for bigger data sets. Otherwise, I mean, you'll be done, okay, and it'll take eternity to complete. So this is called as leave one out, okay, leave one out cross validation. That has a special name. You're leaving one sample out every time. That's what this means, okay. All right, if k is equal to number of samples, this one has a special name. All right, so this is what I wanted to share. I mean, you
Certain,
yes.
sorry to cut you off. Like, if you were taking 100 samples, then like how we give to the train and test. If it is 20, then it is fine. Like we were giving 80 to the test and then 20 to the train.
It is fixed. It is fixed. The number would be fixed as you decide this k. The number would be fixed for train and
No,
test.
I'm asking like if I'm taking my fold as 100, like as we said, like my k as
You'll be using
100.
one in test and 99 in training in every fold.
Okay.
It cannot be changed.
Okay, so if it is 20, then I can put 80 in training, 20 in test.
No. What validation you are doing? How many
so for
folds?
example, like I'm saying my case.
Listen, Dinesh. I'll probably give a statement here, and that will convince you. Okay.
Okay.
The number of samples in training and testing, they are dependent on the number of folds. They are not independent. Okay. The number of partitions that you decide, this will decide how many samples will go to train and test. It is not independent. In every fold, you cannot decide these many samples go to train and test, because if you explicitly decide, then the intersection between the test sets may not be followed. It is not k-fold cross validation then.
Okay, so the partitions will decide, like then the k equal to 5. This will.
Yeah, k equal these will decide, right? So if you have 100 samples, imagine the first 20 samples from 1 to 20. Okay, they are in P1. Okay.
Yeah.
The next 20 samples, 21 to 40, they are in P2.
P2.
And so on. Okay. Is this clear?
Yeah.
I mean, if you want, you can shuffle it and you can pick the first 20. Okay.
Totally.
That you can do. That you can do. Okay.
Have you shared any drive link with all these notes?
Yeah, I did. I believe I did.
Yes, you did.
Do you want me to reshare it?
Yes, please.
Just a second, please. I'll reshare it as well. I just took, I believe, one class only. Okay.
Yes, you did.
So just a second. My system is very slow. Oh, okay. I'll share the drive link in the chat. Okay. You can all bookmark it, and okay, what I'll do is I'll keep everything, like the handwritten notes and everything here itself. Okay. So I'm going to move all these to this July 27. Okay, and I'll make one more folder for today. And I'll put everything. So you can leave if you want to. If you have anything to discuss, we can discuss. Otherwise, you can leave.
Yeah, thank you.
Yeah, take care, guys.
And you said yeah, if a k is equal to the number of samples, then it is called leave
one out.
Leave one out. Okay.
You are leaving one sample in test set every time, right?
Yeah, as you said,
That's
like one goes to testing. Okay.
Your one goes to testing in that case.
Okay.
This one has a special name. By the way, we'll see more types of cross validation as we progress.
Sure.
Okay. Okay, I'll post this. So take care, guys. If anyone has any other questions.
That's it. Thank you, Santon. Have a good day.
You too. Have a good day, Dinesh. Take care. So bye, everyone. I'll post the notes and the code. Okay, in just maybe in 2 minutes. Okay. So bye, everyone. Take care.
Thank you, sir.
Let's see you tomorrow.